Module number 9, this is the chapter 13 in the book, the central limit theorem. All right, I'm going to explain quick the technical issues about this, the technical concepts about this theorem, and then we're going to see many examples. First, if we have n random variables, all of them with mean mu and standard deviation sigma, and all of them are independent and not normally independent and with the same distribution then we define this new random variable given by x1 plus x2 and so on up to xn. This new random variable is called the sampling mean. And this new random variable has its mean is equal to mu. This symbol means the mean of the sampling mean. The mean of this random variable is this one. By the way, it is the same as the mean of the population. And the standard deviation is sigma over square root of n. This is the standard deviation of the sampling mean. The sampling mean. One important note here. The sampling mean, x bar, is a random variable. Do not confuse it with lowercase x bar. This is only the mean of a sample. So in general, this is a random variable. It's called the sampling mean. In the book, you are going to see it like this. This is going to be capital X, and this, do not confuse that random variable with the X bar that is usually represented by lowercase. Capital, lowercase. One is a random variable, the other one is a single number, the mean for a given sample. Well, but there's one very important characteristic about the sample mean. That result is called the central limit theorem. The central limit theorem said that the probability that the sampling mean is less than any number, for example, x0, is the same as the probability that C is less than x0 minus the mean of the sampling mean divided by the standard deviation of the sampling mean. And don't forget, this is the standard random variable with the standard normal distribution. So, in other words, if you want to we can compute probabilities for the sampling mean by using the standard normal distribution. Essentially, that is what the central limit theorem says. But we are, again, this is only like a technical explanation. Essentially, in the exercises we're going to do when we are working with the sampling mean is that we have to compute probabilities almost in the same way as we do it when we computed normal probabilities with normal distribution. But you are going to need to remember, you will have to remember this. The mean of the sampling mean is mu, the same as the mean of the population. Again, the mean of the sampling mean is mu, and the standard deviation of the sampling mean is the standard deviation of the population divided by the square root of n. This is representing all the possible averages for samples of size n. All right, first example. These are examples from a chip. First, classify phrases. In the following hypothetical scenarios, classify each of the specified numbers as a parameter or a statistic. How do we know that? Well, essentially, a parameter makes reference to the population. And a statistic makes reference to the sample. So we're going to need to know that. All right. The first case, it says there are 9 justices currently serving in the United States Supreme Court, and 44% of them were appointed after the year 2000. The 44% here is a what? Well, in this case, I think we can think of the 9 justices as the population, right, of the persons on the Supreme Court. Well, at least as for justices. So in this case, the 44% would be a parameter. The second one. In 1936, Literary Digest polled 2.3 million adults in the United States. So notice, with this word, it's very likely we're talking about what? We're talking about a sample. And actually, it's a sample, right, of all the adults in the United States. So for sure, this has to be with the statistic. And 57% of them said they would vote for F. Landon for the presidency. The 57% here is a what statistic? Next one. The survey results from 12 local parks show the mean height of 60 for mature oak trees. The mean height of 60 is survey that it's very likely made reference to a sample, so it's going to be statistic. Next, the 59 players on the roster of a championship football team have a mean weight of 248.6 pounds with a standard deviation of 44.6 pounds. The 44.6 pounds is what? Well, in this case, the 59 players on the roster of a championship football team, we can say the whole population. So we're going to say here is a parameter. Next, in a random sample of business owners in the United States, it is found that 63% of the sample business owners attend at least one business conference per year. The 63, well, it's saying using the word sample, so for sure this is going to be a statistic. All right, let's continue. Now, the examples. It says, suppose, is an example from a chip. Example, height of male students. Suppose that the distribution of heights of all male students in your campus is normal, with mean equal to 70 inches and standard deviation 2.8 inches. If you choose one student at random, what is the probability that he is between 69 and 71 inches tall? All right, here in this case, x is the random variable representing what? Heights of all male students. The mean is equal to 70 and sigma is equal to 2.8. First, this is asking the question, if you choose one student at random, what is the probability its height is between 69 and 71 inches? All right, for this, we don't have to do nothing new by now because this is only a question about x. So go to Minitab, graph probability distribution plot, view probability, okay, and enter the mean that we got there. Is going to be 70 and the standard deviation 2.8. And then options. Oh, I forgot to write down what we're looking for. So notice it says between 69 and 71. So essentially we look for this. Probability that the high is between 71 and 69. So go to Minitab, specify X value, but use this option middle, so you can enter the two values, 69 and 71. And then OK, and then OK. And the probability, notice this one here, 0.279. 0.279, so go back to the notes, is 0.279. But I see maybe the, just in case you have any problem, the answer from a chip is exactly, because it seems a chip is not using the Minitab or software many times. The answer from a chip is 0.28, but notice it's almost the same, right? 0.279 is rounded up. It's roughly 0.28. Now, what is the standard deviation of X? Well, remember from the formula, the standard deviation for the sample mean is sigma over square root of n. So, standard deviation for X bar is equal to sigma over square root of n. Sigma in this case is equal to what? Is equal to 2.8. So it's going to be 2.8 divided by the square root of n. So it would be this action. This one. This one. You see? And here, X, the sampling mean is all the averages of heights for samples of size n. All the averages of heights for samples of size n. All right. Now, how large an SRS, by the way, this is a simple random sample. How large an SRS must you take to reduce the standard deviation of the sample mean to 0.5? Enter your answer as a whole number. All right, first, the standard deviation of the sample mean is given by sigma over square root of n, but before we saw it was 2.8 divided by the square root of n equal to, and we want this to be equal to 0.5, yeah, because it says how large must you take to reduce the standard deviation of the sample mean to 0.5. So we need to solve this equation. 2.8 divided by the square root of n equal to 0.5. You have to solve for n. It's going to be, if you solve for n, you're going to get that n is equal to 2.8 divided by 0.5 raised to the square. And you are going to get 31.36. But if you round it up to the next whole number, this is going to be 32. So the answer is 32. So we need to take a sample of size 32 to guarantee we will have a standard deviation of the sample mean, this one, equal to 0.5. Now, what is the probability that the mean height of the sample in the previous step is between 69 and 71? In this case, notice it's not the same question, right? It might look similar. The first question to the last question. Here we're using the x only, but here in the next question we have to use this x bar. So we look for the probability that x bar is between 71 and 69. You will be able to compute this by using Minitab. What are you going to need? Only remember that the mean for x bar is the same as the mean of the population. The mean of x bar is going to be 70. This one. The mean of the sampling mean is the same as the mean of the population, always. So this is going to be 70, and you will need sigma x bar that we have computed before. We have to use the previous value, 0.5. So once you have this, you will have to go to Minitab and treat this as if this were a common normal distribution, right? So go to graph, probability distribution plot, view probability, okay. Mean 70, but now change the mean to 0.5. Options, the same value, 69 and 71, okay, okay. And the value you will have is 0.9545. 0.9545. Let's go back to the notes. So this value is 0.9545, but again, Achieve doesn't have the exact answer. The answer from Achieve is supposed to be this one, 0.9566. So this one is from Achieve. But the exact answer is this one. I mean, this is more precise. Yeah, I think, again, I mentioned before why we're seeing the differences. I think because when they put the answers on Achieve, they didn't use a software. Maybe they use a table. But here in this class, since this is online, you can be able to use only Minitab. All right. Now with the same problem, with the same data, with the same information, now we have, suppose that the distribution of heights of all my students on your campus is normal, with mean 70 inches and standard deviation 2.8 inches. So the same information as before. So we're working with the same problem essentially, but we will have more questions. What standard deviation must X bar have so that 99.7% of all samples give an X within 1/2 inch of mu? All right, and it says use the rule 68, 95, 99.7. I mean, this is the empirical rule. All right, so we know that 99.7% of the values fall. If you don't remember this, I recommend to check the notes from the previous module, all right, or the video notes. of the values fall in the interval mu minus 3 times, since in this case we're focusing on x bar, yeah, so we will have to use the distribution for x bar. The mean of x bar is mu, but the standard deviation is sigma over square root of n, comma, mu plus 3 sigma over square root of n. But this, it says, has to be separately 1/2 inch of mu. So we need to have an interval that is mu minus 0.5, comma, mu plus 0.5. Subtract and add. This means 1/2 inch, within 1/2 inch of mu. So this means that if these two intervals are the same, then this is the same, so this value should be equal to this value, see? Then we have this equation. This implies that 3 sigma over square root of n is equal to 0.5. And you will have to use the value before. Sigma, remember, was sigma is 2.8. So we have 3 times 2.8 divided by square root of n equal to 0.5. If you solve for this, you will get n equal to 3 times 2.8 divided by 0.5 raised to the square. And the value you should get, is n is equal to 282.4. This is the value for n. But that is not the question, right? The question for part A is what is the standard deviation? So once you have n, now remember that the standard deviation of the sampling mean is sigma over square root of n. It's going to be sigma, that is 2.8, divided by the square root of 282.4. And you will have 0.6166667, or if you round it up, it's going to be 0.17 inches. So the answer is this one. Now, for the question for the part B is how large an SRS, simple random sample, do you need to reduce the standard deviation of x to the value you found in part A? Notice, we already have the question here. This is the question for the part A, and this one is the question for the part B, 282.4. No, it said we have to round it up to, give me a second. We have to round it up to, well, we have to round it up to the nearest whole number. So in this case, it's going to be 283. There you have 0.17 and 283. Example, blood potassium level. Judith measured potassium level varies according to the normal distribution, with mean equal to 3.8 and sigma equal to 0.2. let's consider what could happen if we took for 4 separate measurements from UD. So here, notice, mu is equal to 3.8, sigma is equal to 0.2, and we're going to take a sample with size equal to 4. 4 separate measurements. 4. What is the blood potassium level L such that the probability is only 0.05 that the average of 4 measurements is less than L? All right, in this case, X bar is all the averages of potassium level for samples of size n equal to 4. So here you have to be careful because notice it says what is the blood level L if you have 0.05. So this is like an example we saw before about we have a probability. How do we compute the observed value? This is why it is saying here this requires an inverse normal calculation. So how do we proceed here? First, I'm going to set up, we look for L such that the probability, notice it says here less, the probability that X bar is less than L is equal to 0.05. So what value of X makes this possible? So you will have to use again Minitab. Go to Minitab, go to graph, probability distribution plot, view probability, okay. Mean equal to, now change the mean. The mean has to be the mean for, all right, let me explain this. You will have to use the mean for X bar. The mean of X bar is the same as the mean of the population, mu, 3.8. But the standard deviation, be careful because it's different. It's going to be sigma over square root of n. In this case, 0.2 divided by the square root of 4, because n is equal to 4, so it's going to be 0.2 divided by 2 equal to 0.1. And there you have 3.8 and 0.1. 3.8 and 0.1. 3.8 for the mean and 0.1 for the standard deviation. Then options, here be careful. We're looking for an observed value, so we have to specify the probability. But be careful as to how to use, you need to use the right tail. This probability should be such that it has to be here, the value for L. So this region here, this is the area we know. This is supposed to be 0.05. So what is the value for L that makes this possible? So go to Minitab and choose left tail, and probability 0.05. Actually, it's given there, 0.05, and then OK, OK. And the value is this one, 3.636. So Minitab, So this is 3.636, but I think we have to round it up to 2 digits. So it's going to be 3.64. And there you have. All right, next example. The United States Center for Disease Control and Prevention, the CDC, found that 17.9% of women ages 12 to 59 test seropositive for HPV-16. Suppose that Tata, an infectious disease specialist, assays blood serum from a random sample of N equal to 1,000 women in the United States, age 12 to 59. Apply the central limit theorem for the distribution of a sample proportion to find the probability that the proportion P hat of women in entire sample who test positive for HPV is greater than 0.204. Express the result as a decimal precise to 3 places. All right. Here, when we have this one, this little thing that is p hat, it's something similar here. Here, p hat is the sample proportion or sampling proportion. P hat in this context is number of individuals who tested positive in the sample divided by the size of the sample, N. But in this case, N is going to be 1,000, right? But the point is that, again, P hat is very similar to the sampling mean. This is a random variable. It's not a number. So how do we proceed with this? The mean for P hat is only the proportion, is equal to the proportion from the population that I'm going to know by P. In our example, is going to be only this one, 17.9%. So we put here 17.9% or 0.179 without percentage. And the standard deviation for this is given by the next formula, the square root of P times 1 minus P divided by N. In our example, square root of 0.179 times 1 minus 0.179 divided by 1,000. So we need this, and we're going to need this. This value is going to be for this one, I got 0.0121227. Try to use as many decimals as possible. I got these decimals. So this is the value for sigma of P, or the proportion sampling, and the mean of the proportion sampling is 0.179. Next, notice you need to compute only this. Probability that the proportion sampling is greater than 0.204. So go to Minitab and don't forget these two values, this one and this one. Again, go to graph, probability distribution plot, view probability, okay. In the mean, you will have to put what? 0.179. And for the standard deviation, 0.012127. Options. Notice it says P hat greater. So it has to be to the right. So you will have to use a right tail. And you will need to specify the X value. The value is 0.204. And then OK, and then OK. And this is the probability we're looking for, 0.01959. So this answer here is, oh, but we have to round it up. So it's going to be 0.01959 or 0.020. This is the right answer. And for the other one, you will have to do the same thing. But now notice, you are going to change the number and the sense of the inequality. So now we do the same. Graph, probability distribution plot, view probability. Okay. Now this is the same. Options. Now we need to use a left tail and change the value of X. That is going to be 0.171. Okay. Okay. And the probability of the area is 0.2447. I mean 0.2547. 0.2547. .2547, or round it up, 0.255. And there you have, that is the answer. All right, that's over now. If you have any question, feel confident to let me know. See you in the next video.